Systems of Particles and Rotational Motion, Part 3. In the last class, we studied about center of mass, the definition of center of mass, and how to find the distance of center of mass from the origin. And we also studied about the position vector for the center of mass. So recalling the formula, the position vector R vector is given by sigma MIRI by capital M. Here MIRI stands for the mass of the ith particle multiplied by the position of the ith particle divided by capital M stands for the mass of all the particles of the system. Now if you cross multiply this expression, we get MR equal to sigma MIRI. I varies from 1 to n. Therefore, when you expand sigma MIRI, it is equal to M1 R1 plus M2 R2 plus up to Mn Rn. Now, if you differentiate the two sides of this equation with respect to time and keeping mass constant, we get m into dr by dt equal to m1 dr1 by dt plus m2 dr2 by dt plus up to mn drn by dt. dr by dt is velocity of the center of mass. r1 dr1 by dt is v1, dr2 by dt is v2, that is velocity of the second particle, and drn by dt is equal to vn, which is velocity of the nth particle. Again, if you differentiate with respect to time, keeping mass constant, we have m, capital M into dv by dt on the left side equal to m1 dv1 by dt plus m2 dv2 by dt plus up to mn dvn by dt. Now dv by dt on the left side will give you acceleration of the center of mass. And dv1 by dt on the right side will give you a1, which is the acceleration of the first particle. dv2 by dt will give you a2, which is acceleration of the second particle, and dvn by dt will be an, which is acceleration of the nth particle. So we have m into a on the left side. M is the mass of the system and a is the acceleration of the center of mass. But from Newton's second law, we know that force is equal to mass into acceleration. Therefore, the right side of the equation can be written as F1 plus F2 plus up to Fn, where F1 is m1 a1, F2 is m2 a2, and Fn is mn an. On the left side, we have mass into acceleration of the center of mass of the system. Thus, the total mass of a system of particles times the acceleration of its center of mass is the vector sum of all the forces acting on the system of particles. So we can write mass into acceleration of the center of mass will be equal to all the external forces acting on the system of particles. Now we must make note that no internal force of the particle is considered here. The internal force of all the particles will add up to 0, and it will have no effect on the center of mass of the system of particles. So therefore, m into a on the left side for center of mass is equal to the sum of all the external forces acting on the particles of the system. So we can conclude the center of mass of a system of particles moves as if all the mass of the system was concentrated at the center of mass and all the external forces were applied at that point. Let us see the example of a projectile in parabolic motion. A projectile is projected along a parabolic path, and on its way it explodes. Now, when it explodes, the explosion is purely due to internal forces within the projectile. It has nothing to do with its projectile motion, parabolic motion. The parabolic motion is due to gravity. So, what happens? All the fragments from the center of mass will just continue along the same dotted lines. Only a few particles will fly off, but the center of mass will move along the same gravitational line. The center of mass of the fragments of the projectile continues along the same parabolic path which it would have followed if there were no explosion. Even if there was no explosion, the particle would have followed the same path. In spite of the explosion also, the fragments follow the same path because the explosion has taken place due to internal forces and not due to external forces. Only external forces can deter the projectile from its path. So let us read the explanation. A projectile following the usual parabolic trajectory explodes into fragments midway in air. The forces leading to the explosion are internal forces. They contribute nothing to the motion of the center of mass. The total external force, namely the force of gravity acting on the body, is the same before and after the explosion. The center of mass under the influence of the external force continues, therefore, along the same parabolic trajectory as it would have followed if there were no explosion. Next is linear momentum of a system of particles. We know that linear momentum is mass into velocity, and linear momentum is a vector denoted by the letter p. And here on the right side, velocity is a vector denoted by v. So p vector is equal to m into v vector. Now we also know that Newton's second law of motion is written as F equal to dp by dt. That means the rate of change of momentum is directly proportional to the external force applied, and it takes place in the direction of the force. So that is Newton's second law of motion for you to remember. So now we have a system of n particles, not a single particle, but we have a system of n particles. The linear momentum of the system can be written as P equal to P1 plus P2 plus up to Pn. So on the left side, P shows the momentum, linear momentum of center of mass. And the right side shows the momentum, linear momentum of each particle. P1 is the linear momentum of the first particle, P2 is the linear momentum of the second particle, and Pn is the linear momentum of the nth particle. They all add up and will be equal to capital P. Now, if you substitute the values of P1, P2 and Pn, you will get capital P equal to M1V1 plus M2V2 plus up to MnVn. We can sum this and write it as P equal to M into V. So, capital P is equal to mass of the system of particles, the total mass of the system of particles, and V is the velocity of the center of mass of the system of particles. So, the total momentum of a system of particles is equal to the product of the total mass of the system, that is capital M, and the velocity of its center of mass, that is capital V. Next, if you still differentiate this expression P equal to mv keeping mass constant, you get on the left side dp by dt when you differentiate it with respect to time. Dp by dt equal to m into dv by dt. But dv by dt is acceleration. So will be equal to mass into acceleration. So this is acceleration of the center of mass. You must understand that the center of mass is also in motion. and m is the total mass of the system of particles. But we already know that just previously we saw that m into a is equal to the sum of all the external forces. So here dp by dt equal to ma and ma equal to external forces F. Therefore, dp by dt is equal to F external, which is Newton's second law of motion. This is extended to a system of particles now. So what happens if P is a constant? If P is a constant, that means the linear momentum of the center of mass is a constant. Of course, you know m is a constant. When can P be a constant? When velocity is also constant, or when the center of mass is moving with uniform motion, we say velocity is constant. So P is constant when mass is constant and velocity is constant. And when you differentiate a constant value, you know you get 0. So dp by dt is 0. When is it 0? When P is constant. And when is P constant? When mass is constant and velocity is constant. Thus, when the total external force acting on a system of particles is 0, the total linear momentum of the system is constant. This is the law of conservation of the total linear momentum of a system of particles. This also means that velocity of the center of mass remains constant, or the center of mass moves with a constant velocity. When velocity is constant, the motion is uniform and there will not be any acceleration. Let us see the example of a radioactive decay of a moving unstable particle. Here we have radium. Radium is radioactive. It is moving and it has its center of mass exactly in the center because it's a single particle. As it moves, it disintegrates. It is radioactive. You must understand it is unstable, so it disintegrates into radon and helium. Helium is otherwise known as alpha particle. So here we have the splitting of radium into radon and helium. Now what happens? The line joining helium and radon. Now this has come to a two-particle system and the center of mass will be closer to the heavier particle, which is radon, among these two. So we have center of mass will still maintain that same line represented by the dotted lines. Even though radon and helium fly apart, the center of mass will still maintain that same dotted line. Okay? Another example, radioactive decay of a particle which is at rest. So here let us imagine that radium, which is radioactive, is at rest. Now when it is at rest and at some point of time it just splits into radon and helium. So the center of mass of radium is here, and even after splitting, the center of mass will be there itself. It will be at rest because radium is at rest, the center of mass is initially at rest, therefore radon and helium will fly back to back and the position of center of mass will be maintained. Now, so much so for the case of binary stars. Binary stars are two stars which have a common force of attraction and they maintain a certain distance among each other. So here binary stars are represented by S1 and S2 and here they are making helical motion. S1 is moving with dotted lines and S2 is moving in solid line. Now when they are always at the same distance from each other, so center of mass will be somewhere along this line if they are of equal mass. See, center of mass is along this line. So whatever position S1 takes and whatever position S2 takes, they will always be diametrically opposite to each other. This distance between S1 and S2 will be maintained. And therefore center of mass will remain in the same position. It will be there itself. All right. trajectories of two stars S1 by dotted line and S2 by solid line, forming a binary system with their center of mass C in uniform motion. Here we have the binary stars again. But here the difference is that center of mass is at rest. So S1 and S2, instead of making helical motion, they just revolve around the center of mass. So what happens? Always the distance from S1 and S2 will be same. They'll be diametrically opposite to each other, and therefore the center of mass will remain in the same position. Let us see one application. We'll read out. A child sits stationary at one end of a long trolley, moving uniformly with a speed v on a smooth horizontal floor. If the child gets up and runs about on the trolley in any manner, what is the speed of the center of mass of the system? Now, what is the system here? The trolley and the child. There is a common system now, trolley and child, and it has a common center of mass. So, will the center of mass change? That is the question. The answer is no change. Now, let us see why it is not changing. The child is running arbitrarily on a trolley moving with velocity v. However, the running of the child will produce no effect on the velocity of the center of mass of the trolley. This is because the force due to the boy's motion is purely internal. Internal forces produce no effect on the motion of the bodies on which they act. Since no external force is involved in the boy trolley system, the boy's motion will produce no change in the velocity of the center of mass of the trolley. I hope you have understood. Okay, children, thank you. We will continue in the next part.